Hey everybody, this little video lesson is going to cover something known as the ideal gas law.
Before we talk about the ideal gas law, we need to talk about a couple of variables that chemists like to use, and a way to do that is to identify them as STP. STP stands for standard temperature and pressure, and it's an easy way for scientists to basically tell you two variables without giving you much more than just three letters. The two variables of standard temperature and pressure are 1 atmosphere of pressure and 273 Kelvin. These pressures and temperatures are standard, means that they're the same all the time. Whenever someone or problem says that a particular sample of gas is at STP, what they mean is it's at 1 atmosphere of pressure and 273 Kelvin. This will come up as you're doing the problems here in the future. What you're looking at now is something called the ideal gas law. It is a gas law used to determine an unknown variable of the ideal gas. Those variables are pressure, volume, temperature, number of moles, and the R constant. And we'll talk about the R constant here in a second. So first of all, pressure is always in atmospheres. So if it's given to you in kPa, you need to convert it to atmospheres. Remember, 1 atm is equal to 101 kPa. So if you have kPa, just divide by 101 and get atmospheres. Volume is always in liters. So if you have milliliters, all you need to do is move the decimal point 3 to the left to convert to liters. Temperature is in Kelvin. So if you're presented temperature in degrees Celsius, add 273 and you will have Kelvin. And finally, N is number of moles. Now, up until this point, we've been talking about a gas law called the combined gas law, and number of moles, or N number of moles, is always held constant. But now, in the ideal gas law, it's a very big deal. It is part of the ideal gas law. And then finally, R is what is known as the ideal gas constant. It is a number that is inserted into the gas law and used to do math. We'll talk about it. I have an entire slide about R here in a second. The gas law is P times V equals N times R times T. And in these problems, you'll be given 4 of the 5 numbers and solve for the missing one. Now, what makes the ideal gas law different than the combined gas law is one basic principle. If I take, for example, and split this screen into two sides when we talk about the combined on the left and ideal on the right, I'll first start by writing out the gas laws separately. Now if you look closely at the combined gas law, we've got P1V1 over T1 equals P2V2 over T2. And what you'll notice is that conditions are changing. And what that means is that you always start with some pressure, volume, or temperature, and it changes over the course of the problem. What to look for when doing a combined gas law problem are 2 pressures or volumes or temperatures, and that's how you know you're doing a combined gas law problem. Now on the other hand, the ideal gas law, or P times V equals N times R times T, you only have one of each variable. And that means that conditions are not changing. So if the problem just sets up a pressure, a volume, a number of moles, and asks you to solve for the temperature, that's an ideal gas law problem. But if it gives you one pressure and asks you about the new pressure when the volume starts from one and goes to another. So notice just the wording of the question typically is longer because you're setting up a set of conditions changing. And that's how you know you're talking about an ideal gas law problem versus a combined gas law problem. And the last thing that people always point out is that combined gas law problems never mention moles. But if you ever see moles in the problem or are asked to solve for moles in the problem, you are dealing with an ideal gas law problem. Now before we do a practice problem, I want to talk to you more about the ideal gas constant. The ideal gas constant is a number that doesn't change. It's always 0.0821. Now I'm going to put this number, actually more like I'm going to put the units of this number in parentheses to separate the number from the units. Now what's also unique about the ideal gas constant is it has 4 units. It's a number with 4 units. That seems strange to a lot of you. In fact, you've never seen anything like this up until this point in chemistry. We've had numbers with individual units, but this is a number that's constant and has 4 units. Now the purpose of these 4 units is that 3 of them cancel out, and 1 does not. The number is always used as a multiplier, and the units are always used to cancel. So in a problem, you'll see when I do the problem in just a minute or two, you'll see that I put in the ideal gas constant with its units, and 3 of the 4 of these will cancel out in the problem, leaving 1 uncanceled, and that makes it the unit in the answer. Now, the most common mistake I see with the ideal gas constant is people think that these units are numbers that need to be placed into the gas constant and then solve for. But in fact, you do not do this. You take this whole thing, number and units together, and place it into the ideal gas law, do the math, cancel the units, solve for the missing variable. Now I'm going to take you through 2 examples of solving for the ideal gas law. The first thing I always like to do, just like I did in combined gas law problems, is set up my variables. Now, this is not the same as the combined gas law, because I'm going to set up the ideal gas law variables. I'm going to set up pressure, volume, number of moles, R constant, and temperature. And right away I can put 0.0821 liters times atmospheres over moles times Kelvin into the R constant. Then I go into the problem and I look for all the other variables, like 2.5 atmospheres, so that's a pressure. I look for temperature, 293 Kelvin, 293 Kelvin. And finally I look for the last number, 0.5 moles. The only number I don't have, which is the number I'm going to solve for, is what's the volume. Set it up. I'm going to scroll down to give myself a little bit of room, and I put in 2.50 atm times V, which is unknown, and that's equal to N, or 0.500 moles, times, here we go, the R constant, 0.0821 liters times atmosphere over moles times Kelvin, finally 293 Kelvin. Now I go in with my red pen and I solve for V by dividing by 2.50 atm on each side. So I take 2.50, 2.50 atm, and check out the units. So moles cancels moles, K from the temperature cancels the K from the R constant, and atmospheres cancels the atmospheres from the constant, and the only one that is left uncancelled out is liters. And that's good because we're going to be solving for V, which is in liters. So now you put this into your calculator. You take 0.5 times 0.0821 times 293 divided by 2.5, and you get an answer of V is equal to 4.81 liters. So for my next problem, I'm going to do the same thing. Let me scroll up, give myself lots of room. Start out with the Pivnert variables. Pivnert, you heard me say that. This is probably the first time. Pivnert, PV equals nRT. The ideal gas law is sometimes referred to as affectionately as Pivnert. It's like if you sound out the word PV equals nRT, Pivnert. So when I say Pivnert variables, I mean I'm going to write out PV nRT down this side. And the first thing I do is put 0.0821 liters times atmosphere over moles times Kelvin. Then I go in and look for my other variables that I have available to me. 3 liters, so that's a volume. I've got 0.9 atmospheres of gas this time. And I've got 325 Kelvin. So the only variable I'm missing is moles. Furthermore, it says how many moles of gas are there. To keep things consistent with my last example, I highlighted in blue how many moles of gas are there. Well, let's set up and solve for N. So we'll take 0.900 atm times 3.00 liters equal N, but I'm looking for that, 0.0821 liters times atmosphere over moles times Kelvin, and finally 325 Kelvin. Now in red, I'm going to actually do my work in red, and the first thing I'm going to do is I'm going to multiply these two together over here, and then I'm going to divide by, and I'm going to multiply by these two over here, and so I can get my numbers smaller and then solve for N. So the first thing I do is multiply the left-hand side, and I get 2.7. Now the units are still atmospheres times liters, but that's fine. Nothing to worry about there. Just leave those there. N is still N, and then on this side I multiply 0.0821 times 325 and I get 26.6825. And the units there are liters times atmospheres over moles. Because the Kelvin from the K temperature and the Kelvin and the R constant cancel each other out. Now what I want to do is I want to divide by 26.6825 liters times atmospheres over moles on each side. 26.6825 liters times atmosphere over moles on each side. And check this out. Liters cancels liters, atmospheres cancels atmospheres, and the only one left is moles. The only thing left to do is divide these two numbers. So I'm going to scroll down and give myself a little bit of room, and N is equal to 0.101 moles of gas. Well, that concludes this quick video lesson on the ideal gas law. Thanks for listening.